We've classified wind turbines on their basic operating principle, either drag or aerodynamic lift type. Wind turbines can also be classified according to the orientation of their rotating axis, either horizontal or vertical. In the lecture on drag-type wind turbines, all of the designs are vertical axis. In the lecture on the fundamentals of aerodynamic lift, all of the examples were for horizontal axis wind turbines. There are also vertical axis wind turbines that operate on the principle of aerodynamic lift, and this lecture will very briefly describe them. There are two main types of vertical axis wind turbines that operate using aerodynamic lift. The blades are airfoil sections just like the blades on a propeller-type horizontal axis wind turbine. The first is the Darius or egg beater design on the left. Only a few large Darius machines have been built. The picture shows an experimental one that was built quite some time ago in Quebec on the shores of the St. Lawrence River. A second experimental Darius machine was built by Sandia Laboratories in the United States. My understanding is that the weakness of the design is a mechanical issue, not a performance issue. Specifically, the bottom rotor bearing must support a tremendous load and was problematic, so that would be in this area down here as to support this entire rotating structure. Neither of these Darius machines mentioned have operated for many years to the best of my knowledge. More promising in the current context is the H-type rotor shown on the right. You can see that this is just a slice out of the Darius rotor with the blades straightened out rather than curved. You can see that this allows the bearing to be placed at the top of the structure, so as the green arrow shows, which greatly reduces the weight that has to be supported by the rotor bearing. There are a number of companies developing smaller H-type rotors, so this type may be relevant in some applications. Let's review a few basics relevant to this particular type of wind turbine. The figure shows an S-type rotor rather than an aerodynamic lift-type rotor, but for this purpose, they are all vertical axis wind turbines. For a vertical axis wind turbine having a rotor of diameter d and height h, the flow area, so this blue rectangular cross-section duct which is surrounding the rotor, is the stream tube. And so for this circumstance, the flow area is actually d times h. So that's different than the other types of wind turbines. So what you should not do, if you look from the top and take pi d squared as the area, that's not correct because the flow isn't going that way. It's going across the wind turbine. So the proper flow area for a vertical axis wind turbine, whether a drag type or whether an aerodynamic lift type, is A is equal to d times h. In all of our wind turbine studies, we have started with the power available in the wind. Note that this formula and many other power formulas contain A, which is the flow area, as noted on the previous slide. So for vertical axis wind turbines, once again remind you that for rotor diameter d and height h area, the flow area is equal to d times h for vertical axis wind turbines. Okay, so the aerodynamics for vertical axis wind turbines, lift type wind turbines, are really complex and beyond the scope of this course. In a previous lecture, we discussed the principles of aerodynamic lift and drag and how they generate force on a cross-section, an airfoil cross-section. And in the vertical axis wind turbine, you can see the blades on the outside of the H rotor, for example. Those are just aerodynamic airfoil shapes, just like the horizontal axis wind turbine. So the principles are the same. You have lift and drag, and components of that apply to turn the rotor. Right, and once again, just like the case of the horizontal axis wind turbine, the propeller type we've previously talked about at some length, the performance depends on rotor speed. So that those characteristics are shared. A characteristic of the vertical axis aerodynamic lift type wind turbine is that the rotor is not self-starting. It doesn't, if the wind is blowing, it doesn't doesn't start moving on its own. So some provision has to be made to initiate rotation. So for example, electrically, you can operate just for a brief moment or two the electrical generator as a motor to turn the rotor up to some speed, and then it generates enough tip speed motion to create the proper wind motion triangle, wind vector triangle, to generate substantial power, right? So that's a technicality that can be overcome, but it just exists. So an interesting strategy for starting, I showed in the introduction this very unusual wind turbine, which actually combines two types of wind turbines. You can see there's an egg beater type design, a Darius type here. There's actually 3 blades, and inside there are stacked two Savonius type rotors. Right, so this is a very interesting combination. Presumably the Darius is for power production in windy conditions, and the Savonius solves the starting problem. It has excellent starting torque and presumably would contribute to low wind conditions as well. The presence of the Savonius in here would certainly have an impact on the flow characteristics of the Darius wind turbine. So this is certainly a compromise situation, and I have no information about how well this particular type performed. So let's just briefly summarize with this very brief look at this aerodynamic lift type of vertical axis wind turbine. Let's briefly summarize the characteristics. So the aerodynamic lift type vertical axis wind turbines can have excellent performance. We're going to have some data on that in the next lecture on performance measures. There are still some design challenges with vertical axis wind turbines, but perhaps not surprising considering that far more resources have been spent on developing horizontal axis wind turbine. The propeller type technology has been going on for a really long time and has also benefited from much aircraft work. Smaller power aerodynamic lift type vertical axis wind turbines are under development and may play a larger role in the future. However, we do need a strategy for starting these devices. With this very brief look at aerodynamic type vertical axis wind turbines, please proceed to the lecture on wind turbine performance measures.